Hello, I welcome you all in this course on mechanical measurement systems. Today we will discuss first order system impulse response. First order system first order system impulse response. As all of you know, the impulse is exerted when a large amount of force is put on a body or exerted on a body for a very short duration of time. By Newton's second law of motion, force is defined as rate of change of momentum, or can be defined as m delta v by delta t. Fine. When this rate of change of momentum is same and delta t is very small, we are going to feel, or the object is going to feel, very high order of force, because force is again m dv by dt. So this change in momentum is for very short time. Suppose, for example, there is a wall and we are striking a ball on the wall. When the ball strikes the wall, then within no time there is a change in the direction. When there is a change in direction, mv, suppose the momentum is mv, the change in momentum becomes 2mv, right? Because there is a change in the direction of the velocity and for very short duration of time. And this is how the impact loading is done on the wall through a ball. But in electrical signals, impulse loading can be understood as a pulse. Suppose there is a pulse, we are measuring again voltage with the help of a voltmeter. All of a sudden there is a pulse, right? And the pulse remains for a very short time, or delta t or dt for pulse tends to 0. Now how the system will respond, how our measuring instrument, which is of the first order, will respond to this pulse. So for this we will do one analysis. Now in this analysis we will assume that the pulse is for a finite duration of, let us say, t. And in the pulse the energy is important, because it lasts for a very short duration of time. And suppose this is area, it is depicted by this area. Shape of pulse is not that important, because either it will have a flat this or this or this. It will not have much bearing on the A, right? So shape of the pulse is not very important, because it lasts for a very short duration of time. And this is PT. Now it is a limiting process and it has a functional strength of A, right? And magnitude in this direction, the y direction, we can always assume as A by T, right? And when the A is unit, when A is equal to 1, then it becomes unit impulse function, and unit impulse function can always be expressed by del t, or any impulse function can be represented by A del t. Now we will not focus on this, we will focus on system response. System response, because it is, I reiterate that, because it is for a very short duration of time, shape of the pulse is not that important. It will last only for, let us say, 1 microsecond, right? But we assume it to be we assume it to represent by a rectangle having an area A, and it lasts for a duration of time t. So magnitude in this direction, PT direction, is going to be A by T. Fine. Now here I will read out this diagram. Now here it will act as a terminated step response. We can divide this in two regions. One is this region where input signal is there, and another region where there is no input signal. Or there are two boundary conditions. One is t is less than t, and one is t is greater than t. Regarding the response of the system, because all of a sudden there is a step input, fine. So, but the system cannot be respond this manner, right? For a step input, it will rise the response of the system, the output will rise until before it attains the final value, because this t is much smaller than the time constant. So, before it attains the final value, the input is removed and the system will again respond like this. It will not go below this. So, it will rise and then again it will fall. Now, if we make t to t by 2, now t is reduced to t by 2, then this amplitude will be doubled and the system response will again be like this, right? Now, we'll now mathematically we'll express the system response in this case. To begin with, we'll take this part of the impulse. This part of the impulse will start with qo is equal to k qi 1 minus e raised to power minus t by lambda, and this is limiting up to here. Now, input qi, so here the qi we shall take as a by t. So, qi is going to be equal to k a by t 1 minus e raised to power minus t by lambda, right? Now, for this part we do not have any standard equation, right? But since it is a first order system, we will assume that, or we will take that lambda d plus 1 qo is equal to k qi. This is the generalized equation for first order response of the first order system. Now, in this part, input is 0. So, this part is 0. When this is 0, then complementary function q complementary function is going to be equal to c e raised to power minus t by lambda. Because lambda d plus 1, we can say lambda d plus 1 is equal to 0, and for this equation will have only one root, and for one root complementary function is going to be like this. Now, particular integral will not be there because this side is 0. So, the solution for this equation is q O is equal to c e raised to power minus t by lambda, provided t is greater than t or equal to t, right? And here also we will take greater than equal to, and this is less than or equal to, less than or equal to. Now, we have to find the value of c, which is unknown, and we don't have, earlier we used to have boundary conditions, but here we have boundary conditions at infinite time. This output is going to be 0, but it will not be used here. So, in order to find c, what we can do at this point, this particular point, both of these equations are valid. So, what we will do here, we will put t is equal to t and we will equate these two equations. Once we are putting t is equal to t, capital T, t is time. So it means Ka by t 1 minus e raised to power minus t by lambda, capital T by lambda, is going to be equal to C e raised to power minus capital T by lambda. Now in this equation, the unknown is only C. So C is Ka by T 1 minus e raised to power minus T by lambda divided by e raised to power minus capital T by lambda. Now T is known to us. So we can say that an impulse of a short duration may be 1 microsecond or 1 millisecond. We can go up to 1 millisecond also. So 1 microsecond, 1 millisecond. So for that short duration, the normal value T is going to have. Now just put this equation C here. When you are putting this value of C here, then we are getting Qo is equal to Ka by T 1 minus e raised to power minus capital T by lambda divided by e raised to power minus capital T by lambda e raised to power minus small t by lambda. This is the response of the instrument. So there is a volt, suppose in electrical system there is a voltmeter and there is a pulse in the voltage. So voltage suppose shoots, so a normal voltage is 200 volts, all of a sudden it shoots to pulse maybe of let us say 1000 volts or 2000 volts, and this pulse remains for a very short duration of time. How the system will behave, this is after the pulse, this is going to be the governing equation, right? Now in this governing equation, we have assumed T as some infinitesimal time, but in ideal case, this is an approximation, right? Ideal case, what is going to happen to this T? This T should be tending to 0. T should be tending to 0. In fact, the input to the system, this has to be only a pulse, vertical line. This is pulse, right? Because we cannot have this delta t 0, that is why we have assumed that there is a ramp response and it is ramp input, sorry, not ramp input, this is a step input. There is a step input for a very short duration of time, and after that short duration of time, the input is terminated. And then we are seeing how the system is going to respond. Now t is tending to 0, so here Qo we can take Ka by e raised to power minus t by lambda, and then 1 minus e to power minus t by lambda by t e raised to power minus t by lambda. I have just rearranged these values, right? I have just taken t here and t by lambda. The reason being, and the limit t is tending to 0. Because when we are putting the limits, then this term will become 1. So it is Ka. What about this term? Limit t is tending to 0, 1 minus e raised to power capital T by lambda divided by t, and then again e raised to power minus t by lambda. This term, this particular term, it will turn out to be 1 minus 1 divided by 0, that is 0 by 0. Now, in order to cope with this situation, there is a rule, and that is a known as La Hospital rule. And in La Hospital rule, that is La Hospital, both numerator and denominator both will be differentiated. So when we differentiate both and put the value here in this equation, the final expression we are going to get QO is equal to KA, KA is here, and when we differentiate this we will get lambda e raised to power minus t by lambda. This is the final expression we are going to get here. So this is exact. This is exact solution. Approximate solution is, I have given you earlier, for this part of the response, the approximate solution is QO is equal to KA by T 1 minus e raised to power minus t by lambda divided by e raised to power minus t by lambda e raised to power minus t by lambda. This is the approximate solution. So this is the approximate solution. In this solution, we have simply taken limit tending to 0 and we have got exact solution. Now, how different is this exact solution is from approximate solution? Now, we'll do one analysis. Now, in this analysis, we will study the impulse response for a particular case. Now, for particular case means there is an impulse for duration t. In this impulse, the response of the instrument is going to be like this, for example. For this reason, when 0 is less than equal to t is less than equal to capital T, it will act as a first order system. The first order system means QO is equal to K QI 1 minus e raised to power minus t by lambda, and QI we have already assumed or we have taken as A by T, right? Now T we have taken as here assumed as 0.01 lambda. So QO is going to be equal to Ka by 0.01 lambda, right? And 1 minus e raised to power minus t by lambda. Or we can say that QO is 100 K, A we can take 1, right, divided by lambda 1 minus raised to power t by lambda. That is one case. Another case is we take approximate solution. Approximate solution is, that is one case. Now approximate solution is QO is equal to K, A we have already taken 1, divided by, multiplied by 100, divided by lambda, because it is 0.0, because t is replaced by 0.01 lambda. So Ka by T e raised to power minus 0.01 and 1 minus e raised to power minus 0.01 multiplied by e raised to power minus t by lambda. This is approximate. This is out of the approximate solution. Approximate solution is Ka by T 1 minus e raised to power minus capital T by lambda divided by e raised to power minus capital T by lambda e raised to power minus small t by lambda. So just we have replaced the values here because capital T by lambda is 0.01. So 0.01 we have placed here, and this is our approximate solution, right? So now we have these two solutions. We can have exact solution also. The exact solution here is, because exact solution is QO is equal to Ka by lambda e raised to power minus t by lambda. Fine. Now A again is 1 and lambda we have taken as t multiplied by 100. And this is multiplied by 100. Now we have these two solutions. One is approximate, one is exact. This one, there is no issue with this solution because this is well established. Now there are issues whether this is correct or this is correct, or either of this can be taken. When the time is less than capital T, this will operate, and when the time is greater than capital T, when time is greater than capital T, then we can take approximate as well as exact solution. Now we will compare approximate solution with exact solution. Now when t is equal to 0, now this is, let us take this as approximate or exact and approximate, and let us take the value of t by lambda, value of t by lambda, and the value of q by k by t, and this is also q divided by k by t, right? So q divided by k by t, so q o divided by k by t will give e raised to power minus t by lambda. So when t is equal to 0 or t by lambda is equal to 0, right, then in this case, this is approximate and exact. This is exact solution. So exact solution is going to be what? 1. Exact solution is 1. When t by t is equal to, the response of the system is going to be like this. Now for this reason, we can always take first order system, the step response to the first order system, and step response to the first order system means QO is equal to KQI 1 minus e raised to power minus t by lambda. Now we are assuming that t is equal to 0.01 lambda. It is only 1% of time constant of the instrument. So when we are assuming t is equal to 0.01 lambda, and for this we have already taken Qi as k a by t 1 minus e raised to power minus t by lambda, and t is equal to 0.01 lambda. So it is k a 0.01 lambda 1 minus e raised to power minus t by lambda, and this is going to be equal to QO is equal to 100 Ka divided by lambda 1 minus e raised to power minus t by lambda. Now we will write here QO by K by lambda is equal to, for a is equal to 1, suppose we take a is equal to 1, it is going to be equal to 100 1 minus e raised to power by t by lambda, right? Now the second one is beyond this we have another approximate solution, and that approximate solution is QO is equal to Ka by t 1 minus e raised to power minus t by lambda divided by e raised to power minus t by lambda. This is approximate solution for this region. So when we take approximate solution for this region, and this is multiplied by e raised to the power minus t by lambda. Now, if we take approximate, and here we have already noted that t is equal to 0.01 lambda, or we can say t by lambda is equal to 0.01. So, Q is equal to, again, K, A we have assumed 1, capital T is 0.01 lambda, 1 minus e raised to power minus 0.01 divided by e raised to power minus 0.01 multiplied by e raised to power by lambda. Or we can assume that again here we can write Qo by k lambda, k by lambda is equal to 100, 1 minus e raised to power 0.01 divided by e raised to power minus 0.01 and raised to multiplied by e raised to power minus t by lambda. K has come here and k by lambda has come here, right. So this is valid for t is less than or equal to t is less, and this is valid for there are two cases. So for any pulse we can find the solution using these two cases, these two values. Now before this we have derived one equation, and that equation is Qo is equal to, that is the exact solution. If you remember, we have derived one equation for exact solution for impulse, and that is Qo is equal to Ka by lambda e raised to power minus t by lambda, right. And here if we take Qo by k by lambda is equal to e raised to power minus t by lambda. So either we get solution out of this, or we take solution by single equation, that is Qo is equal to Qo by k by lambda is equal to e raised to power minus t by lambda, or we can use singly this equation. So this equation is valid for entire range. Now we will take the different value of t by lambda and we will calculate true impulse and approximated impulse. Let us start with 0. So if we take t by lambda is equal to 0, then true impulse is going to be 1, and approximated impulse will come from here and it is going to be 0. Now we will take t by lambda as 0.001. When we take t by lambda as 0.001, then here we will be getting 0.999 and approximated impulse is 0.1. Then we will come to 0.01, here we will be getting 0.990 and here we will be getting 0.995. Now this is becoming closer to this approximated. Again, if we take 0.1, then for 0.1 it is 0.905, 0.913. Now we can continue to have 0.2, 0.819 and 0.826, right. Now 0.5, 0.607, 0.612, 1, 0.368, then 0.372 and we can go 5, then 0.00674 and 0.00681. What I want to show you here is that initially true value is 1, because the impulse t is tending to 0. So if you draw the graph, then initially the pulse is 0. Sorry, the pulse is 1 at t is equal to 0, ideally. So QO k by delta, true value is this 1, approximated value is 0, because it is a step response. So initially we are considering a step response. So step response at t is equal to 0, the output is 0. Then 0.001, right? Then it is coming 0.1, then 0.01. They almost become equal to each other. So the response, the true response of the instrument is like this. But if you look at the approximated response of the instrument, it will be something like this. Because in the rest of the terms, you see the difference is not much. So approximate solution is also as good as true solution, right? So error is very little, infinitesimal, right? So this is how the system behaves when it comes under impulse input, and initially it has to be infinite. Ideally, it has to be infinite, right? So we have taken Q by k by lambda as 1. It has not infinite. It has to have unit value, and this will start from 0, and within very short duration of time, this will reach the 0.995. Okay. Now, in addition to this, when the pulse is for very short duration, the shape of the pulse does not matter, right? It is only energy that is imparted to the instrument, and we can take one. We can mathematically also we can ensure this. Let us take first order system. It is lambda d plus 1 QO is equal to QI, KQI. Or lambda dQO by dt plus QO is equal to KQI. Or lambda dQO plus QO dt is equal to KQI dt. Fine. Now this QI dt is area. This is K multiplied by area. So it is K multiplied by area. Now we will integrate this. Now we will integrate this equation from 0 to 0 plus. 0 to 0 plus, right? And this will also get integrated QI dt 0 to 0 plus. Now we have taken this, already considered this QI dt as area, and when we integrate this, we get lambda QO minus 0 plus it is QO. At t is equal to 0 it is QO, and t is equal to 0 plus it is QO, and this is going to be 0 is equal to K multiplied by area. Area we have taken unit area for the sake of analysis, right? So we can say that QO at 0 plus is K by lambda, right? So when it is K by lambda, right, and this is the value when the time is equal to 0 plus, just before the starting. 0 plus means just before the starting, right? Now, if there is a impulse, so impulse signal can also be represented as a differential of step input. Suppose in an instrument there is a step input. If I differentiate this signal, I will be getting a vertical line, right? Or if, because in actual practice, the step input is not like this. Step input is, it is something like this. When it is something like this, then this vertical line will become a dome, right? So step input, if you differentiate step input, you will get impulse signal. Perfect step input will give you, differentiation of perfect step input will give you perfect this impulse signal. If you integrate this again, you may get step signal. Okay, this is how this can also be represented, and this is all for this lecture. In the next class, we will start with the frequency response of first order systems.